Tonight, you are going to find out that the hardest part of going to Mars is not getting there, it is getting back. This is the part of the conversation that gets quietly skipped in every documentary, every news segment, every announcement about humans on Mars. We talk about the launch, the 9 months, the landing, the boots on red soil, and then the conversation ends as though arriving were the end of the story. It is not. The moment those boots touch Mars, every law of physics and every limit of engineering converges into one quiet truth, that getting them home is harder than getting them there, by a margin so wide that the second man to walk on the moon has spent decades arguing they should not even attempt to come back. Tonight we walk through why. If these slow cosmic walks help you settle before sleep, a quiet subscribe means a lot. We begin. There is a particular kind of mission in the history of exploration that almost nobody talks about clearly when it is happening. It is the mission where the destination is real, the funding is real, the engineers are real, the rockets are real, and the people stepping aboard the spacecraft are real. But the return journey, when you look at it carefully, is not. That is the mission to Mars. This is not a statement made by skeptics or people opposed to space exploration. It is a statement that emerges quietly and consistently when you sit with the actual numbers that govern what it would take to send humans to the surface of another planet and bring them back alive. The numbers do not say going is impossible. The numbers say returning is what becomes newly impossible. And the gap between those two ideas is where the entire conversation tonight lives. For most of the modern era of spaceflight, the assumption has been that any human mission worth attempting is, by default, a round trip. You go, you explore, you come home. That model worked for the moon, where Apollo astronauts left, performed their missions over hours or days, and returned. It works for the International Space Station, where astronauts rotate in 6-month shifts. It works because the distances are small enough, the energy requirements modest enough, and the timeline short enough that returning is part of the same engineering problem as going. Mars is not in that category. Mars is far enough, requires enough energy, takes long enough to reach, demands long enough on the surface, and presents enough biological and engineering obstacles that the return half of the trip is not just harder than the outbound half. It is a different kind of problem entirely. The going half is a transportation problem. The coming back half is an engineering miracle, wrapped in a biology problem, wrapped in an economics problem, wrapped in a chemistry problem. When the first humans arrive on Mars, they will arrive with a ticket that has only been half issued. The other half, the return half, will exist on paper. It will exist as a plan. It will exist as a hope. It will not, in any way that the universe recognizes, exist as a guaranteed event. This is the quiet truth that aerospace engineers know, and most public conversations do not. Tonight, we are going to walk through why, not as a tragedy, not as an argument against going to Mars, as a calm, careful examination of what it actually means to send people to another planet and what the structure of that mission looks like when you stop assuming the return half is automatic. It begins, as nearly everything about Mars does, with distance, because before you can understand why coming back is so hard, you have to understand what you are coming back from. And the distance, it turns out, is doing more work in this story than almost anyone realizes. Mars and Earth are not at a fixed distance from each other. This is the first thing that surprises people who think carefully about the topic. We talk about Mars as though it sits at a specific distance from us, in the same way we talk about the moon being roughly 384,400 kilometers away. But Mars does not work that way. Mars and Earth are both moving in elliptical orbits around the Sun at different speeds, and the distance between them is constantly changing. At their closest, when both planets are on the same side of the Sun and lined up in their orbits, Mars can come within approximately 54.6 million kilometers of Earth. This is called opposition, and it happens approximately every 26 months. At their farthest, when Mars and Earth are on opposite sides of the Sun, the distance balloons to roughly 401 million kilometers. The average distance, the number cited in most textbooks and reference materials, is approximately 226 million kilometers. That range from 54.6 million to 401 million is not a small variation. It is a factor of more than 7. The distance to Mars at its farthest is more than 7 times the distance to Mars at its closest. This single fact governs more about Mars mission architecture than almost any other variable. Because spacecraft cannot simply pick the closest moment and launch, the relative positions of the planets, their orbital velocities, and the energy required to transfer from one orbit to the other all combine to create what aerospace engineers call a launch window, a narrow span of time when the geometry of the solar system permits a fuel-efficient trip. The 54.6 million kilometer minimum distance, while real, does not represent what you experience on an actual mission. By the time your spacecraft arrives at Mars, both planets have moved. Mars is not where it was when you launched. Earth is not where it was either. The path your spacecraft follows is not a straight line from where Mars was to where Mars is. It is a curved trajectory through space, calculated to intercept Mars at the moment Mars arrives at the meeting point. This is why the average distance, 226 million kilometers, is the useful number. It represents roughly what a real mission deals with, integrated across the trajectory and the variable positions of the two planets. And it is the reason why a one-way trip to Mars takes around 9 months, even though light from Mars reaches Earth in anywhere from 3 to 22 minutes depending on positions. The Moon, by comparison, sits at a relatively fixed average distance of 384,400 kilometers. Mars is roughly 588 times farther away on average. The Apollo missions, traveling at speeds that would seem modest compared to interplanetary spacecraft, reached the Moon in about 3 days. Mars takes 9 months at comparable propulsion efficiency because the distance is so much greater that even doubling or tripling the speed would still leave you with a journey measured in months, not days. This is the distance that defines the mission, not the closest approach, not the farthest, but the average that any real spacecraft has to negotiate. 226 million kilometers, traversed at speeds of around 24,000 kilometers per hour during cruise, taking 9 months to complete. And the distance is only the first constraint. The second constraint, the one that genuinely shapes what kind of mission is even possible, is when you can leave at all. Because the universe does not let you go to Mars whenever you feel like it. It lets you go on a schedule, and that schedule is the rhythm of the entire conversation tonight. In 1925, a German engineer named Walter Hollmann published a book titled, in translation, The Attainability of Celestial Bodies. It was a quiet work, written by a man whose day job was as a city building inspector in the German town of Essen. He worked on the mathematics of interplanetary travel in his spare time, with no expectation that any of his calculations would ever be applied to a real mission. He was simply solving the problem because he found it interesting. The book described what is now called the Hohmann transfer orbit, the most fuel-efficient way to travel between two circular orbits around a central body. The mathematics is elegant. To move a spacecraft from Earth's orbit to Mars's orbit, you do not aim it at Mars, you aim it along a curved elliptical path that touches Earth's orbit at one point and Mars's orbit at the other. The spacecraft coasts along this ellipse, accelerated once at the start of its journey and once at the end, and the rest is gravity doing the work. The Hohmann transfer is the cheapest way, in fuel terms, to get from one planet to another. Almost every Mars mission ever launched, from Mariner 4 in 1965 to Perseverance in 2021, has used a Hohmann transfer or a slight variation of it. The reason is simple. Any other trajectory requires substantially more fuel, and fuel is the single most expensive thing to lift off the surface of Earth. The catch with Hohmann transfers is timing. The orbit only works when the two planets are in specific relative positions at the moment of launch. Earth has to be at the start of the ellipse. Mars has to be at the point where the ellipse will intersect Mars's orbit, but time so that Mars itself arrives at that intersection point at the same moment the spacecraft does. This alignment is what astronomers call a synodic period, the time it takes for two planets to return to the same relative positions in their orbits. For Earth and Mars, the synodic period is approximately 780 days, about 26 months. Every 26 months, the planets return to the configuration that allows a Hohmann transfer, and a brief launch window opens for spacecraft to depart Earth for Mars. Miss the window and you wait another 26 months for the next one. This is the rhythm Mars demands. Every 26 months, a launch window opens, lasts for a few weeks, and closes. During that window, a spacecraft can leave Earth efficiently. Outside the window, the trip becomes prohibitively expensive in fuel terms, or simply impossible without exotic propulsion systems we have not yet developed. Now consider what this means for a crewed mission. If you launch from Earth during a Mars window, you arrive on Mars approximately 9 months later. By the time you arrive, the relative positions of Earth and Mars have shifted. Earth has continued in its orbit. Mars has continued in its orbit. The geometry that allowed your launch from Earth no longer applies to a launch from Mars back to Earth. To return to Earth using another Hohmann transfer, you have to wait for the planets to realign in the reverse configuration, the configuration that allows a fuel-efficient trip from Mars to Earth. That return alignment, due to the geometry of the two orbits, does not occur immediately. It does not occur in 2 weeks or 2 months. It occurs approximately 500 days after your arrival on Mars. 500 days after your arrival on Mars. 500 days. About 16 months. 16 months of waiting on the surface of another planet, not because you want to wait, but because the universe has structured the orbital geometry such that you cannot leave until that specific alignment occurs. This is the second constraint. Distance was the first. The 26-month rhythm is the second. And it is during those 500 days on the Martian surface that almost everything else in this conversation begins to go wrong. There is a particular kind of waiting that humans have never experienced before in the history of our species. Every form of waiting we know on Earth has an option built into it. You can leave the place where you are waiting. You can change your mind. You can walk out the door, drive to the airport, send a message asking for help. There is always, in every situation a human being has ever been in on Earth, a theoretical exit. Even astronauts on the International Space Station can, in an emergency, board a return capsule and be back on Earth in hours. The first humans on Mars will not have any of this. For 500 days, give or take, they will be on the surface of a planet they cannot leave, not because they do not want to, not because no one will come for them. Because the geometry of the solar system does not permit a return trip until the next Mars-to-Earth window opens. The spacecraft that brought them is sitting on the surface, perhaps still intact, perhaps not. The fuel for the return journey is either being manufactured locally, slowly, from the Martian atmosphere, or it does not yet exist at all. Either way, leaving is not a choice. It is a future event scheduled by the laws of orbital mechanics. This is what aerospace engineers call a conjunction-class mission, named because the launch window for return occurs when Earth and Mars are in conjunction on the same side of the Sun. A conjunction-class mission is the long-stay version of a Mars trip, with about 500 days on the surface and the lowest total energy cost. The alternative, called an opposition-class mission, allows for much shorter surface stays of 30 to 90 days, but requires far more fuel and produces a much riskier mission profile, often passing closer to the Sun on the return leg and increasing radiation exposure substantially. For any realistic crewed mission, the conjunction-class architecture is the only viable option, which means 500 days on the surface by default, not because that is the desired duration, because that is the duration the universe imposes. 500 days is longer than most military deployments, longer than most expeditions to Antarctica, longer than the typical tour of duty aboard the International Space Station, longer than almost any sustained human isolation that has ever been documented in deliberate scientific study. The closest analogue we have is the Mars 500 experiment conducted in Moscow between 2010 and 2011, in which 6 volunteers spent 520 days inside a sealed habitat simulating a Mars mission. We will return to what they discovered later in this conversation. The findings are not reassuring. But 500 days is not the worst of it, because during those 500 days the human body and the technical equipment supporting it are both deteriorating in measurable, documented ways that the universe does not pause to accommodate. The body in particular has a problem that begins long before the crew even arrives on Mars. It begins the moment they leave Earth, and it continues throughout the journey, and it does not stop when they land. By the time the surface stay is complete, the bodies of the first Mars crew will be substantially different from the bodies that left Earth. Some of those changes may be reversible. Some, almost certainly, will not. To understand what 500 days on Mars actually does to a human, we have to start with what 9 months of spaceflight to get there does first. Because that journey, the journey out, is where the damage begins, and the damage, once it begins, accumulates in ways that compound across the entire mission. The human body did not evolve for space. This statement sounds obvious, almost too obvious to mention, but the implications of it are profound and have been documented by NASA, the European Space Agency, and Roscosmos across more than 60 years of crewed spaceflight. Every system in the human body, from bones to muscles to fluids to cells, is calibrated to function in the gravitational field of Earth. Remove that gravity even partially, and the body begins to change. Sometimes the changes are minor and reversible. Sometimes they are not. The most thoroughly studied change is bone loss. In microgravity, weight-bearing bones, the bones that on Earth carry the load of the body against gravity, begin to lose mineral density. The mechanism is straightforward. Bones are living tissue. They constantly remodel themselves, with cells called osteoblasts building new bone, and cells called osteoclasts breaking old bone down. On Earth, the mechanical stress of gravity stimulates osteoblast activity, keeping the bone-building and bone-resorbing processes in rough balance. In microgravity, that mechanical stress disappears. The osteoblasts slow down. The osteoclasts continue at their normal rate. The result is a net loss of bone density. NASA's measurements, accumulated over decades of long-duration missions on the International Space Station, show that astronauts lose approximately 1 to 1.5% of bone mineral density per month in weight-bearing bones. More recent studies, including a 2020 systematic review in NPJ microgravity, report that the loss can reach 1.5 to 2% per month in the femur and lumbar spine for missions longer than 6 months. A 9-month flight to Mars would, at these rates, produce a cumulative bone density loss of somewhere between 9 and 18% in the weight-bearing bones. That is the kind of loss that on Earth would take a typical adult decades of aging to accumulate. It would, in many cases, be diagnostically equivalent to osteoporosis. A 2022 study published in Scientific Reports examined 17 astronauts who had spent 4 to 7 months in space. Those who flew longer than 6 months had permanent bone loss in their tibias, the shin bones, equivalent to about a decade of aging. Muscle loss accompanies the bone loss. Without the resistance of gravity, postural muscles, the muscles that on Earth maintain the body's upright position against gravitational pull, atrophy rapidly. Studies of astronauts after 6-month ISS missions showed 20 to 30% decreases in muscle mass, particularly in the lower extremities. The calves, the thighs, the lower back, the muscles you would need most to walk on the surface of another planet. Astronauts on the ISS spend approximately 2 hours per day on exercise equipment, including resistance machines, treadmills, and stationary bikes, specifically to slow the bone and muscle loss. The exercise helps. It does not eliminate the problem. After 6 months, even with 2 hours of daily exercise, measurable bone loss still occurs. For a Mars mission, the 9-month outbound journey would impose this damage before the crew even arrives. They would land on Mars, in 38% of Earth's gravity, in bodies that have already lost between 9 and 18% of their weight-bearing bone density. They would have lost roughly a quarter of their relevant muscle mass. They would step out of the lander in a place where they will have to perform physical labor, set up equipment, conduct experiments, and survive for 500 days, with bodies that are physiologically weaker than they have been at any point in their adult lives. And the Mars surface gravity, while present, is only 38% of what they trained in. Whether that 38% is enough to halt the deterioration or only enough to slow it is one of the most important open questions in the entire field of long-duration spaceflight medicine. And the honest answer as of right now is that nobody knows for certain. When the first crew stepped out of the lander onto the Martian surface, they will weigh roughly 1/3 of what they weighed on Earth. This is not a minor detail. The gravity on Mars is approximately 0.38 times the gravity on Earth, or 38%. A 70-kilogram astronaut on Earth would experience the equivalent of about 26 kilograms of gravitational pull on Mars. Walking would feel different. Lifting equipment would feel different. The body's entire mechanical experience of being in the world would feel different. The question is whether 38% of Earth gravity is enough to halt the bone and muscle deterioration that began in microgravity. This question, as straightforward as it sounds, has never been answered. We have decades of data from microgravity, which is approximately zero gravity. We have all of recorded human biology from Earth, which is 1 full gravity. We have essentially no data on what happens to the human body at the intermediate values of lunar gravity, which is about 0.16 g, or Mars gravity, which is 0.38 g. The reason is simple. No human has lived long-term in either of those gravitational environments. The Apollo astronauts visited the moon for hours or days, never long enough for chronic biological effects to manifest. No one has ever lived on Mars at all. The data that would tell us whether 0.38 Gs is sufficient to maintain bone density and muscle mass does not exist. There is a theoretical threshold, sometimes referred to in space medicine as the 0.67 G threshold. This number comes from research suggesting that something approaching 2/3 of Earth gravity may be the minimum needed to prevent significant deconditioning of bones, muscles, and the cardiovascular system over long durations. The 0.67 G figure is not definitive. It comes from limited experimental data, primarily from ground-based studies using bed rest and centrifuge experiments, but it suggests that Mars gravity at 0.38 G may fall short of the threshold needed to maintain the body in something resembling Earth normal condition. If this hypothesis is correct, the implication is significant. A crew arriving on Mars after losing 9 to 18% of their bone density during the cruise would not regain that density on the Martian surface. They might continue to lose density. They might stabilize at the reduced level. They might recover partially. We do not know which, and the implications for return are even larger. If the body cannot maintain itself in Mars gravity, then 500 days on the surface means 500 more days of compounding deconditioning, on top of the 9 months of damage from the cruise. By the time the return launch window opens, the crew's bodies may be in significantly worse condition than they were when they landed. The return cruise another 9 months in microgravity adds more loss. The crew arrives back at Earth, if they make it back, with bodies that have spent more than 2 years in environments below the gravity threshold that maintains them. Earth's gravity, on return, would feel crushing. Astronauts who spend 6 months on the ISS describe Earth, on return, as feeling impossibly heavy. They struggle to stand. They cannot walk steadily. Their cardiovascular systems, calibrated to microgravity, fight to maintain blood pressure in the now overwhelming gravitational field. Recovery takes weeks. For some functions, like full bone density, recovery takes years and may never be complete. For a Mars crew, after more than 2 years away from Earth's full gravity, the return adjustment would be far more severe. Some specialists have suggested it might be unsurvivable for some crew members. Others suggest it would be survivable but require months of physical therapy. The honest answer, again, is that we do not know. No human has ever returned from a multi-year stint in low or zero gravity. The first Mars crew would be the experiment. This is the gravity problem. And it leads directly into something larger, because beyond gravity, beyond the body's deterioration in microgravity and in Mars's reduced gravity, there is another force acting on the crew throughout their entire mission. A force that is not visible, not felt, but measurable, documented, and, by NASA's own standards, in excess of the safety limits the agency places on its own astronauts. Inside the spacecraft, throughout the 9-month journey to Mars, the crew will be exposed to an invisible flux of high-energy particles streaming through the cosmos. These particles are called galactic cosmic rays. They originate from supernova explosions and other high-energy astrophysical events across our galaxy, and they travel through space at nearly the speed of light. On Earth, we are largely shielded from them by 2 layers of protection: the atmosphere, which absorbs most of them before they reach the surface, and the magnetosphere, Earth's magnetic field, which deflects them away from the surface entirely. Beyond Earth's magnetosphere, the protection ends. A spacecraft in interplanetary space is subjected to the full force of galactic cosmic rays, with no atmosphere and no magnetic field to filter them. NASA's Curiosity rover, launched in 2011, carried an instrument called the Radiation Assessment Detector. During its 253-day cruise from Earth to Mars, the detector measured an average daily radiation dose of approximately 1.8 millisieverts. Millisieverts are the unit used to quantify biological radiation exposure, calibrated to reflect the actual damage that radiation does to living tissue. To put 8 millisieverts per day in context, the average background radiation that a person receives on Earth is approximately 3 millisieverts per year. The radiation dose in transit to Mars is, per day, roughly 2/3 of an entire year's worth of Earth's surface radiation. Per day, for 253 days after the rover landed on Mars, the same instrument measured the radiation dose on the Martian surface, approximately 0.264 millisieverts per day, lower than the cruise dose because Mars provides some shielding, particularly from below, where the planet's mass itself blocks radiation, but still high. Still many times the Earth's surface background. When you combine the cruise dose with the surface dose over a planned mission of 360 days of travel and 500 days on the surface, the cumulative radiation exposure comes to approximately 101 sieverts. 1 full sievert accumulated over the mission duration. 1 sievert is a number with specific medical meaning. The European Space Agency caps the career radiation exposure of its astronauts at approximately 1 sievert because 1 sievert is associated with roughly a 5% increase in lifetime fatal cancer risk. NASA's own standard caps career astronaut exposure-induced death risk at 3%, evaluated at the upper 95% confidence interval. A Mars mission, as currently architected, would expose each crew member to a radiation dose that exceeds NASA's career limit. In a single mission, the career exposure limit, designed to be the maximum a human astronaut should accumulate over an entire career of spaceflight, would be exceeded by 1 trip to Mars. This is not a small overshoot. This is not a margin that can be brought into compliance with better shielding or shorter missions. The galactic cosmic rays that produce most of this dose are so energetic that conventional spacecraft shielding does not stop them. A spacecraft wall made of aluminum, for example, can actually make the problem worse, because high-energy cosmic rays striking aluminum produce secondary radiation called secondary particles that compound the biological dose. To meaningfully shield against galactic cosmic rays, you would need either a very massive shield on the order of several meters of water or hydrogen-rich material which is far too heavy to launch, or you would need to find some way to actively deflect the particles using a magnetic field, an active shielding concept that has been studied but never built for spaceflight. In the absence of either of those solutions, the radiation dose is what it is, approximately 1 sievert per Mars mission, exceeding NASA's career exposure cap, increasing each crew member's lifetime cancer risk by something in the range of 5 to 10%, possibly more, depending on individual sensitivity and which models you use. This is the first absolute wall in the cage we're building tonight. Not a wall of physics that says return is forbidden, a wall that says, by NASA's own standards, the radiation alone makes the mission a one-time event for each astronaut. They cannot do it twice. The agency would not permit it, and it's only the first of the compounding constraints. Because while the radiation is doing its work on the body, the engineering required to actually leave Mars is presenting an entirely different category of problem. In 1903, the same year that the Wright brothers achieved powered flight, a Russian schoolteacher named Konstantin Tsiolkovsky published an equation that would, decades later, become the mathematical foundation of every rocket ever built. The equation describes the relationship between the mass of a rocket, the mass of its fuel, the speed at which that fuel is ejected, and the final velocity the rocket can achieve. It is elegant in its form and brutal in its implications. The equation says that to achieve any given change in velocity, the amount of fuel required does not grow linearly with the velocity target. It grows exponentially. For small velocity changes, the fuel requirement is modest. For large velocity changes, the fuel requirement becomes punishing. And for the velocity changes needed to leave the surface of one planet, travel through interplanetary space and land on another, then do the reverse trip back, the fuel requirements become so large that the entire mission architecture has to be designed around them. Consider what happens when you want to launch a rocket from Earth's surface and reach Mars. You need fuel to lift off Earth. You need fuel to break free of Earth's gravity. You need fuel to perform a transfer maneuver to reach Mars. You need fuel to slow down at Mars and either enter orbit or land on the surface. Each of these maneuvers requires fuel, and each kilogram of fuel for a later maneuver has to be carried along during all the earlier maneuvers, which means you need additional fuel just to carry the fuel. This is called the rocket equation's tyranny, and it is the reason why the Saturn V rocket that sent astronauts to the Moon was roughly 96% fuel by mass at launch. Now apply the same logic to a Mars return mission. To return from Mars, the crew needs fuel to launch from the Martian surface back into Mars orbit. They need fuel to perform a transfer maneuver from Mars orbit back to Earth. They need fuel to slow down at Earth. The total amount of return fuel is substantial, comparable in many ways to the fuel needed to launch from Earth in the first place, because Mars's gravity, while weaker than Earth's, is still substantial, and the velocity changes required for interplanetary return are large. Here is the compounding problem. All of that return fuel has to be present on Mars when the crew is ready to leave, which means it either has to be launched from Earth, carried along on the outbound trip, landed on Mars, and stored on the surface for 500 days before being used, or it has to be manufactured on Mars from local resources after the crew arrives. The first option, launching all the return fuel from Earth, multiplies the Earth launch mass requirement enormously. Every kilogram of fuel you need to lift off Mars has to first be lifted off Earth, transported to Mars, and landed on the Martian surface intact. The Tsiolkovsky equation, applied to this scenario, produces fuel mass requirements at launch from Earth that are, in most plausible mission architectures, simply impractical. The vehicle would be so large, the fuel mass so vast, that no rocket currently designed could lift it. The second option, manufacturing the return fuel on Mars, is the only architecture that makes the mission viable. It is the option that essentially every serious Mars mission proposal, from Robert Zubrin's Mars Direct in the 1990s to modern NASA architectures and SpaceX Starship concept, has adopted. You arrive on Mars with empty fuel tanks for the return trip. You make the fuel there from the Martian atmosphere and from water in the regolith. And then you leave. But this option introduces an entirely new category of problem, because manufacturing rocket fuel on the surface of another planet, at the scale required for human return, has never been done. The technology exists at experimental scales. It has been demonstrated for a few hundred grams of oxygen production. It has never been deployed at the tons per day scale that a crewed return would require, and there are good reasons to suspect that scaling it up will be substantially harder than the current proposals assume. This is where the next part of the story unfolds, not in the rocket itself, but in the device that does not exist yet, but which the entire mission's viability depends upon. There is, on every realistic Mars mission diagram, a particular spacecraft drawn at the center of the surface operations. It sits on Martian soil, waiting. It is the vehicle that will lift the crew off Mars when the return window opens. It is called the Mars Ascent Vehicle, or MAV. It has never been built. This is not a minor caveat. The Mars Ascent Vehicle is, in many ways, the keystone of the entire mission architecture. Without it, no one comes home. With it, the return becomes a real engineering problem rather than an impossibility. And yet, despite decades of conceptual work, despite multiple NASA studies, despite serious proposals from aerospace engineers, no Mars Ascent Vehicle has ever been constructed, launched, or tested in flight. The reason is that the design requirements are exceptionally demanding. A Mars Ascent Vehicle has to do something that no spacecraft has ever done before. It has to be launched from Earth, landed on the surface of Mars, sit on that surface for at least 500 days, exposed to dust storms, temperature swings, and radiation, then ignite its engines reliably on command and reach Mars orbit. To reach Mars orbit, it needs to achieve a velocity of approximately 5 kilometers per second relative to the surface, called the delta V, which is the change in velocity required to break free of Mars's gravity and enter a stable orbit. 5 kilometers per second is not a casual number. It is roughly 12,600 kilometers per hour. To produce that velocity, the MAV needs substantial fuel. The crew compartment, life support, and other necessary equipment all add mass that the fuel has to lift. The vehicle has to be reliable enough that a single failure does not strand the crew on Mars permanently. NASA has studied Mars ascent vehicles intensively, primarily in the context of the now effectively cancelled Mars sample return mission. The MAV for that mission, designed only to lift a few hundred grams of rock samples, not human crew, was envisioned as a two-stage vehicle weighing roughly 400 kilograms with fuel, using a solid rocket first stage and the liquid bipropellant second stage. Even this small sample-only MAV was considered one of the most technically demanding components of the sample return mission. And even that mission, with its small unmanned vehicle, has been delayed, cost overrun, and as of 2026 effectively defunded. A crewed Mars ascent vehicle would be roughly 2 orders of magnitude larger than the sample return version. It would need to carry 4 to 6 crew members in a pressurized cabin with seats, life support, communication systems, and minimal supplies. It would need to be capable of operating after a year and a half on the surface, with fuel that has either been manufactured in situ or stored cryogenically for the duration. It would need to integrate with whatever Mars orbit infrastructure exists to take the crew home from there. No such vehicle has been designed in detailed engineering form. There are conceptual designs. There are proposals. There are computer simulations. There is no engineering qualification model. There is no flight test article. There is no manufacturing program currently underway in any space agency to build one. For perspective, the typical development timeline for a complex crewed spacecraft from initial design to first flight is somewhere between 10 and 20 years. The Space Shuttle took about a decade. The Orion capsule has been in development for nearly 2 decades. Starship, SpaceX's Mars-relevant vehicle, has been in active development since the mid-2010s and has not yet completed a crewed mission of any kinds. A Mars ascent vehicle, given the demands of its operating environment and the lack of comparable prior systems, would likely require at minimum a 15-year focused development program. If serious work began today, on a fully funded basis, the earliest realistic flight test would be in the late 2030s or 2040s, and even then the vehicle would arrive on Mars with empty fuel tanks, because the fuel itself, the propellant that would actually power the launch from Mars back to space, has to be made on Mars, from a planet's atmosphere, using equipment that also does not yet exist at the scale required. This is the next layer of the problem. The fuel that does not exist, made by machines that do not exist, on a planet no human has stood on, to power a rocket that has not been built. And remarkably, all of these problems have been studied. The chemistry is solid, the engineering plausible. The scaling, however, is where everything becomes difficult. In 1897, the French chemist Paul Sabatier discovered a reaction that would, more than a century later, become central to the question of whether humans could ever return from Mars. The reaction is simple. Take carbon dioxide. Take carbon dioxide. Take hydrogen. Heat them together in the presence of a nickel or ruthenium catalyst. The result is methane and water. The reaction is called the Sabatier process, and it has been used in industrial chemistry for over a century. What makes it relevant to Mars is the composition of the Martian atmosphere. Mars's atmosphere is approximately 95% carbon dioxide. The most abundant compound in the air of Mars is exactly the input to the Sabatier reaction. If you can find or import hydrogen, you can make methane and water on Mars. The methane is rocket fuel. The water can be split through electrolysis into hydrogen and oxygen. The hydrogen can be fed back into the Sabatier reaction. The oxygen can be used as an oxidizer for the methane. The result is a self-contained chemistry, producing on Mars exactly the propellants you need to fuel a rocket back into space. Methane and oxygen. This concept is called in situ resource utilization, or ISRU, and it is the single technology that makes any Mars return mission theoretically possible. Without ISRU, the fuel for the return trip would have to be launched from Earth, dramatically multiplying the launch mass, the cost, and the technical difficulty. With ISRU, the crew arrives on Mars with empty return tanks and fills them up locally, using sunlight, water, and the planet's own atmosphere. NASA's Perseverance rover, which landed on Mars in 2021, carries an experiment called MOXIE, The Mars Oxygen In Situ Resource Utilization Experiment. MOXIE is roughly the size of a car battery. It demonstrated for the first time that oxygen could be produced from Martian atmospheric carbon dioxide. Over a series of runs between 2021 and 2023, MOXIE successfully produced small amounts of oxygen, demonstrating the basic chemistry works in actual Martian conditions. This was a genuine achievement, the first time humans had produced a usable resource on another planet. But the scale tells the story. MOXIE produced approximately 6 to 10 grams of oxygen per hour during its operating sessions. Over its full set of demonstrations, it produced a few hundred grams total. A crewed Mars return mission would require, by typical mission architecture estimates, somewhere between 25 and 30 tons of propellant for the ascent vehicle alone. Tons, not grams. The scale gap between what MOXIE demonstrated and what a crewed return mission would need is approximately 5 orders of magnitude. Closing that gap is not impossible. It is in essence an engineering scaling problem rather than a fundamental chemistry problem. The Sabatier reaction works. The electrolysis works. The atmosphere is available. What is needed is a large-scale ISRU plant capable of producing propellant at industrial rates that can be landed on Mars, deployed, powered, and operated for the duration of the surface mission. This plant would not be small. Producing 25 to 30 tons of propellant in a reasonable time frame, perhaps a year or two of operations, would require an industrial-scale chemical processing facility with power, likely nuclear, because solar panels on Mars produce reduced output due to dust and the planet's greater distance from the Sun. With water sourcing. Most architectures assume the plant uses water ice mined from the Martian regolith, with substantial storage, because cryogenic methane and oxygen must be kept at very low temperatures, which means insulation and refrigeration. None of this exists. The MOXIE experiment proved the chemistry. Building the plant remains an engineering project of substantial complexity, with no current development program at any space agency. Estimates of when a full-scale ISRU plant might be tested on Mars range from the mid-2030s in optimistic projections to the 2050s in more realistic ones. And remember that all of this, the plant, the power source, the water mining equipment, the fuel storage, has to be landed on Mars before the crew arrives. Prepositioned. Operational. Produtioned. Operational. Producing fuel, or the crew arrives at a location with no return propellant and no immediate way to make it. This is the architecture that almost every realistic Mars mission proposal depends upon, and it brings us to the heart of the engineering wall. The wall that, more than any other, makes the return trip the dominant constraint of the entire mission. Stop and consider for a moment the actual sequence of events that has to occur for a crew to return from Mars. Long before the crew arrives, a series of robotic missions have to land cargo on Mars. The cargo includes the Mars ascent vehicle itself, sitting on the surface with empty fuel tanks. The cargo includes the in situ resource utilization plant, a chemical processing facility capable of producing methane and oxygen at the rate needed to fuel the ascent vehicle. The cargo includes a power source, almost certainly a small nuclear reactor or a very large solar array, because the ISU plant requires substantial sustained electrical power. The cargo includes water extraction equipment because the Sabatier reaction needs hydrogen, which comes from water, which has to be mined from the Martian regolith. The cargo includes cryogenic storage tanks because the methane and oxygen, once produced, have to be kept at extremely low temperatures, around -162 Celsius for methane and -183 Celsius for liquid oxygen, until they are used. All of this has to be landed on Mars, intact, operational, and then it has to begin producing fuel for many months, possibly more than a year, before the crew arrives. By the time the crew lands, the return vehicle has to be fully fueled and ready to launch, or they cannot leave. This is the engineering wall in its most concrete form. The total mass of cargo that has to be prepositioned on Mars before a single human steps onto its surface is enormous. Let's put it in perspective. The largest Mars ever successfully landed on Mars is the Perseverance rover in 2021 at approximately 1,025 kilograms, about 1 ton 5 kilograms. About 1 ton. That was a single rover with no return vehicle, no fuel plant, no power source. Just a robotic explorer. A crewed Mars return mission requires landing, separately and reliably, perhaps 30 to 80 tons of cargo across multiple precision landings before the crew arrives. The ascent vehicle itself, perhaps 10 to 20 tons. The ISRU plant, perhaps 5 to 10 tons. The power source, depending on whether it is nuclear or solar, 2 to 15 tons. Water mining equipment, storage tanks, spare parts, backup systems, habitat, supplies. We have never landed anything resembling 30 tons on Mars in a single piece, let alone done it multiple times in a coordinated mission. The reason is what aerospace engineers call the Mars entry, descent and landing problem, commonly abbreviated EDL. Mars has just enough atmosphere to make ballistic re-entry impossible. The atmosphere produces too much heating to skip and not enough drag to slow you down efficiently. Spacecraft entering the Martian atmosphere have to use a combination of heat shields, parachutes, retro-rockets, and, in the case of the recent rovers, an elaborate sky crane system. Every method becomes substantially harder as the payload mass grows. For payloads above approximately 2 tons, conventional parachute systems no longer work. The atmosphere is too thin to decelerate the spacecraft enough before impact. New techniques are required. For payloads of 20 or 30 tons, those new techniques have to be developed, tested, and qualified for crewed missions. SpaceX's Starship architecture proposes to solve this with a combination of aerodynamic braking and propulsive landing using the vehicle's own engines. This approach is theoretically feasible, but has never been tested at Mars. The total mass that has to arrive intact in working order, in the correct relative locations on the surface, before a crew can plausibly attempt return, is so far beyond current Mars landing capabilities that some aerospace experts consider it the single largest technical barrier to crewed Mars exploration. Larger than the radiation problem, larger than the bone loss problem, larger than the propulsion problem in many ways. Because all of those problems become tractable if you can pre-position enough infrastructure. And pre-positioning enough infrastructure is, by any honest assessment, decades away from current capability. This is the second wall. The first was radiation, a problem of biology. The second is mass, a problem of engineering scale. And remarkably, both of them combine with a third, which is not biology and not engineering. It is the economics of what doing all of this actually costs. And the most recent evidence on that front is not encouraging. In 2021, NASA's Perseverance rover landed in a place called Jezero Crater on Mars and began an extraordinary mission. The rover was tasked with searching for signs of ancient life, but it had a second, equally important purpose. It was instructed to collect samples of Martian rock and soil, store them in carefully sealed tubes, and cache those tubes on the Martian surface for future retrieval. The samples were intended to be returned to Earth by a follow-on mission. That mission was called Mars Sample Return, abbreviated MSR. Mars Sample Return, abbreviated MSR. Mars Sample Return was on paper one of the most exciting space science projects of the modern era. For the first time, samples of Martian material would be brought to Earth for analysis in laboratories. The scientific potential was enormous. The samples might confirm or rule out the past presence of life on Mars. They would, at minimum, transform our understanding of Martian geology and atmospheric history. But Mars Sample Return required something that had never been done. It required landing a spacecraft on Mars, collecting the samples, lifting them off the surface, transferring them to an orbiter, and returning that orbiter to Earth. 5 distinct missions, integrated across more than a decade, with technical demands that pushed beyond anything humanity had attempted in robotic exploration. The cost estimates began at approximately $5 billion. Within a few years, they had grown to $6 billion. By 2023, an independent review board concluded that the total mission costs could reach $11 billion, with the samples returning no earlier than 2040, $11 billion for a few hundred grams of rock, returned by a robotic mission with no humans involved. The reaction was immediate. NASA's other planetary science missions, smaller projects studying Venus, The outer planets and asteroids were being squeezed to fund the ballooning MSR budget. The Veritas mission to Venus was delayed. The Da Vinci atmospheric probe was delayed. The Dragonfly mission to Saturn's moon Titan saw cost increases of its own. Mars sample return was, in the words of one planetary scientist, becoming the lion feeding on the carcass of the rest of planetary science. In April 2024, NASA Administrator Bill Nelson announced that the current MSR architecture was no longer viable. The cost was too high, the timeline too long. NASA solicited new proposals from industry, hoping to find a cheaper, faster path to bring the samples home. The new options, presented in January 2025, would have brought costs back to approximately $7 billion, with sample return in the mid to late 2030s. But even that was too expensive. In early 2026, the spending package passed by the US House of Representatives effectively eliminated funding for the future MSR missions. The Perseverance rover continues to collect samples. Those samples sit on the surface of Mars in their carefully sealed tubes with no funded plan to retrieve them. The Chinese Space Agency, meanwhile, has announced its own Mars sample return mission, Tianwen-3, targeting 2031. If successful, China would become the first nation to return Martian samples to Earth. The story of Mars sample return is instructive in a way that goes far beyond the science of Mars. It demonstrates that even a robotic mission with no human passengers, no life support, no return habitat, can become so expensive and so complex that the world's leading space agency cannot bring it home. The total cost of bringing back rocks by purely mechanical means has proven to be in the same financial range as the James Webb Space Telescope. If returning rocks from Mars cost $11 billion and may never happen, what does returning humans cost? The honest answer is that we do not know, because no detailed mission architecture for human return has been costed at the level of fidelity that MSR underwent. But scaling laws in aerospace engineering are not gentle. Crewed missions typically cost 5 to 10 times more than equivalent robotic ones. A human Mars return mission would, by any reasonable extrapolation, run into the hundreds of billions of dollars, possibly approaching $1 trillion. Spread across multiple launches, multiple landings, multiple agencies, possibly multiple nations. This is the economics wall. And it leads directly to a particular kind of conclusion that some of the most experienced figures in space exploration have already arrived at. A conclusion that, when stated plainly, sounds shocking, but which, when examined, follows quite logically from everything we have established so far. In 2009, in the pages of Popular Mechanics magazine, Buzz Aldrin, the second human being to walk on the moon, made a statement about Mars that received considerably less attention than it deserved. He argued that the first crewed mission to Mars should not include a return trip, not because returning was impossible, but because the cost of returning was so much higher than the cost of going, and the value of staying so much higher than the value of coming back, that the entire economic logic of human Mars exploration shifted when you considered settlement rather than visitation. Aldrin's estimate, based on his decades of involvement in aerospace planning, was that a return mission costs roughly 3 to 4 times more than a one-way mission of comparable scale. Chris Kraft, the legendary NASA flight director who oversaw Mercury, Gemini, and Apollo, estimated the multiplier even higher, up to 10 times. A return capability, in Kraft's assessment, could increase the mission cost by an order of magnitude. To understand why the multiplier is so large, you have to think about what return capability actually requires. It is not a simple addition, it is a cascade. To return, you need a Mars ascent vehicle. Adding the ascent vehicle adds mass. The ascent vehicle itself, fueled, weighs perhaps 30 tons or more when its fuel is loaded. To deliver that vehicle to Mars requires either landing a similar mass on the surface or manufacturing the fuel locally, which requires landing an ISRU plant and power source on the surface, which adds more mass. Each ton of additional landed mass requires substantial additional Earth launch mass to deliver. The Tsiolkovsky equation, applied iteratively, multiplies everything. You also need to design every piece of the mission for symmetric reliability. A one-way mission only has to work once, in one direction. A round-trip mission has to work twice, in opposite directions, with the return half occurring 2.5 years after launch in equipment that has been exposed to space and Mars surface conditions for that entire duration. Every component must be designed for that lifetime. Every system must be redundant. Every failure mode must be considered. And then you need to bring the crew home, which means designing a return capsule capable of Earth entry from interplanetary speeds, which means high-performance heat shielding, which means precise navigation across hundreds of millions of kilometers, which means accurate atmospheric entry at exactly the correct angle, because too steep means the capsule burns up, and too shallow means it skips off the atmosphere and continues into deep space. All of this multiplies the cost, the mass, the complexity, and the failure modes. Aldrin's argument, then, is essentially an economic one. He is not against humans going to Mars. He is against a particular mission architecture, the round-trip architecture, that he believes consumes resources disproportionate to its value. His proposal is that humans should go to Mars to stay. The crew should go to build, to establish, to begin the long process of human presence on another world. They should be supplied, supported, eventually joined by additional crews, and the return capability should be deferred, perhaps indefinitely, until a self-sustaining settlement exists from which return is no longer the urgent question. This is the position Aldrin has held for nearly 2 decades. He has stated it in op-eds, in interviews, in books. He calls it Mars to Stay, or establishing human permanent presence at Mars. He is not alone. The proposal has been echoed by other prominent figures, including the cosmologist Lawrence Krauss, who wrote in a 2009 New York Times op-ed that to boldly go where no one has gone before does not require coming home again. The aerospace engineer Robert Zubrin, founder of the Mars Society and designer of one of the most thoroughly developed Mars mission architectures, has consistently argued that human Mars exploration should focus on settlement rather than visitation. These are not fringe voices. These are people who have spent their careers thinking carefully about how humans can actually reach Mars. And when they look at the costs, the complexities, the multiplier of return capability, they arrive at the same conclusion. The first mission should be one way, not because the universe forbids return, because the economics of including return, multiplied by all the other constraints we have already discussed, push the mission across the line from barely feasible to almost certainly not happening within any reasonable planning horizon. The proposal, when you state it plainly, is jarring. The first humans on Mars should not come back. They should stay. They should build. They should be the first true settlers of another world. It sounds extreme, but the math as you sit with it suggests it may be the most realistic option. In December 2010, 2 scientists, Dirk Schulze-Mercury of Washington State University and Paul Davies of Arizona State University, published a paper in the Journal of Cosmology titled, "To Boldly Go, a One-Way Human Mission to Mars." The paper proposed exactly what its title suggested, a one-way mission with crew members who would go to Mars knowing they were not coming back. The paper argued that this was not only the most realistic mission architecture, given the constraints we've already discussed, but also the most historically consistent. The authors pointed out that virtually every major human migration in history, the Polynesians settling the Pacific, the Pilgrims arriving in North America, settlers crossing the Atlantic to South America, was one way. The settlers did not arrive expecting return passage. They arrived expecting to build. The proposal generated significant attention. National Public Radio interviewed the authors. Buzz Aldrin echoed the position publicly. The idea, previously considered fringe or unethical, began to be discussed as a legitimate option in mainstream aerospace conversations. The objections were also significant. Critics argued that sending humans on a one-way mission was a form of assisted suicide, regardless of the consent involved. Others argued that the engineering challenges of one-way settlement were just as severe as those of return missions, because settlement requires the same fuel, manufacturing, life support, and infrastructure development as return capability, just maintained indefinitely rather than for a discrete return trip. The supporters had counter-arguments. The infrastructure required for settlement, they argued, would be developed gradually, supplied by repeated robotic missions delivering food, equipment, and eventually additional crew members. The first mission would establish the basic habitat and survival capabilities. The second mission, 2 years later, would add to them. The third mission would expand them further. Over a decade or two, a small permanent settlement would develop, capable of supporting itself with growing independence from Earth. This is, in essence, Robert Zubrin's Mars Direct architecture, modified to remove the return capability and focus on incremental settlement. Zubrin himself, while supporting return missions in principle, has acknowledged that the practical path to sustained human presence on Mars is settlement-focused rather than visitation-focused. "It's Plymouth Rock," he told a PBS Nova interviewer in 2010. "You keep on reinforcing them with more people, more equipment, more of everything, until you have a substantial settlement." The historical precedent is striking. When the Mayflower arrived at Plymouth in 1620, no return passage was planned for most of the passengers. They had come to build. They had come to stay, and while many of them died in the first winter, the settlement persisted, was reinforced by additional ships, and eventually became permanent. The pattern repeated across the Atlantic, the Pacific, the various waves of human migration throughout history. The first arrivals did not come back. They built. They struggled. Some died. Their descendants became the local population. This is the proposal as its serious advocates stated. The first humans on Mars are not visitors. They are pioneers. They go knowing they will not return. They go because that knowledge is what makes the mission practical. Without the return capability, the mission becomes financially and engineering-wise tractable in a way that round-trip missions simply are not. The crew, in this framework, is chosen accordingly. Volunteers who understand the nature of the mission. People prepared to live the rest of their lives on Mars. They are not condemned. They are not abandoned. They are not abandoned. They are part of an ongoing program that will, over decades, build a permanent human presence on another world. They will be supplied. They will be supported. Additional crews will join them. They will, in time, develop something like a community. When Aldrin states this position, he is not advocating cruelty. He is advocating clarity. He is suggesting that the round-trip architecture, with its multiplier of cost and complexity, is preventing humans from actually reaching Mars at all. By accepting the one-way nature of the first mission, the budget, the engineering, and the political support all become achievable. By insisting on return capability, the mission keeps getting pushed further into the future, possibly indefinitely. It is a proposal that turns the question of return from a technical question into a values question. Are we willing to send humans to Mars knowing they will not come back? If yes, the mission becomes possible. If no, the mission may never happen. And whoever those first humans are, they will face something that the Mars 500 isolation study, conducted in Moscow between 2010 and 2011, only partially captured. The reality of being there, with each other, alone, truly alone, for the rest of their lives. Between June 2010 and November 2011, in a sealed facility at the Institute of Biomedical Problems in Moscow, 6 volunteers conducted one of the most ambitious isolation experiments in the history of space science. The project was called Mars 500. Its goal was to simulate, as faithfully as possible, the psychological and physiological conditions of a crewed Mars mission. 6 men, 3 Russians, 2 Europeans and 1 Chinese citizen lived inside a mock-up spacecraft for 520 days. They had no external visitors, no fresh air, no sunlight other than artificial lighting. Their only contact with the outside world was through a delayed communication system simulating the time lag of actual Mars distance. Family contact was limited and lagged. Medical issues had to be handled internally. The Mars 500 experiment was not perfect. There was no microgravity. There was no real radiation exposure. The crew knew throughout the experiment that they were on Earth and that the experiment would eventually end. These were significant deviations from a real Mars mission, but in the dimension of long-duration isolation, of confined quarters living with the same small group of people for nearly 17 months, Mars 500 was the closest analogue ever conducted. The results, as documented in subsequent peer-reviewed papers, are sobering. The crew's activity levels declined dramatically over time. In the first 3 months, the men maintained relatively active routines. By the end of the first year, their activity had dropped substantially. On the simulated return journey, the second half of the experiment, the crew slept significantly more than they had on the outbound journey. By some measures, 700 hours more sleep. Distributed across the return leg, 4 of the 6 men were reported to have suffered from sleep disturbances and psychological issues. Some had difficulty with circadian rhythms. Some experienced periods of depression or social withdrawal. The crew dynamics changed over time as well. Researchers documented what they called adverse personal dynamics, emerging gradually within the group. Small irritations accumulated into significant interpersonal frictions. Subgroups formed. Social distance increased. The crew, while professional and capable throughout, exhibited the kinds of psychological adaptation that emerge whenever small groups are confined together for extended periods. The leader of the experiment, Dr. Tmorth, Boris Morokov, commented in subsequent interviews that any future psychological support system on a real Mars mission would need to be tailored to each individual crew member. Group-based approaches, the assumption that crew dynamics could be addressed at the team level, did not adequately capture the diversity of individual responses. Now consider what Mars 500 was not. It was not a real Mars mission. The crew knew they were on Earth. They knew the experiment would end. They knew their families were a few kilometers away. They knew that emergency intervention was possible if anything went seriously wrong. A real Mars crew, particularly a one-way crew, would have none of these comforts. They would know they were truly alone on another planet with no possibility of immediate help, no certain return, no way to abandon the mission. The psychological pressure by any reasonable extrapolation from Mars 500's data would be substantially greater. A real Mars crew would not eat with their families again. They would not see their parents age. They would not attend weddings of their nieces and nephews, the graduations of their friends' children. They would have communication with Earth, but with a lag of up to 22 minutes one way at maximum separation, and they would be receiving messages from a planet they would never touch again. Their world would be the habitat, the crew, the narrow strip of Martian surface they could explore in suits. This is not a hypothetical. This is the operational reality of a one-way Mars mission. The crew chosen for such a mission would have to be selected specifically for their ability to accept this reality and function within it. Not just for a few months, not for a few years, for the remainder of their lives, however long that turns out to be in the Martian environment. The Mars 500 study, despite all its limitations, demonstrated that even motivated volunteers, under simulated conditions, experience significant psychological strain over 520 days. The implications for a longer, more committed, less supported real mission are not subtle. They are stark. And they introduce a dimension to the return question that is rarely discussed in technical mission planning. Even if return were possible, the psychological condition of the crew after years on Mars would have to be evaluated. They might choose not to come back. They might be unable to return to Earth psychologically, even if they were physically capable. This dimension of the journey, the inward one, is where the Mars mission becomes something stranger than a technical problem, and it leads naturally to another, related dimension. The simple fact that, while on Mars the crew is alone in a way that no human being has ever been alone before. Consider what it means to have a conversation across the distance between Earth and Mars, when the planets are at their closest, approximately 54.6 million kilometers apart. A radio signal traveling at the speed of light takes roughly 3 minutes to make the journey. When the planets are at their farthest, on opposite sides of the Sun at approximately 400 million kilometers apart, a radio signal takes about 22 minutes one way. The average, across a mission of 26 months, is somewhere between 12 and 14 minutes one way. A round-trip communication, a question sent from Earth to Mars and the response received back, takes anywhere from 6 to 44 minutes. At the average distance, around 25 to 28 minutes. Almost half an hour for a single exchange. This means several things in practice. Real-time conversation is impossible. There is no way to have a back-and-forth exchange, because by the time your response to a question arrives on the other planet, the conversation has already moved on by 22 minutes or more. Astronauts on Mars would not be able to call home and talk to family the way ISS astronauts can. They would not be able to have video chats with their children, watch their children respond to what they just said, and respond back. The conversational rhythm that humans have evolved over millions of years simply cannot function across that distance. Communication becomes asynchronous. Every message becomes a small monologue, recorded and sent, received hours or minutes later, then responded to with another monologue, sent back. The Mars crew would have what amounts to a sophisticated email system with the people they left behind. Not a phone call, not a meeting. A series of letters sent across millions of kilometers, accumulating in the inbox of the recipient on the other planet. Emergency response cannot exist in any meaningful form. If something goes wrong on Mars, the crew cannot call mission control for immediate guidance. They send a message. They wait. The message arrives. Mission control on Earth analyzes the situation. They formulate a response. They send the response. The crew receives it. Anywhere from 6 to 44 minutes have passed. For a slow-developing problem, this is workable. For a fast-developing emergency, this is essentially no help at all. The crew must be able to handle emergencies on their own, in real time, with whatever resources they have on the surface. This is fundamentally different from any other human exploration mission. IS astronauts with light-speed communication have effectively real-time support from the ground. Antarctic researchers, while remote, can reach assistance within hours. Submarine crews can surface and signal in minutes. Mars crew cannot do any of this. They are, in the moment of any actual emergency, alone. The Apollo astronauts experienced a small version of this. Communication with the Moon involves a delay of about 1-3 seconds each way. This is fast enough for conversation, slow enough to be noticeable. It introduced a slight unease into Apollo communications, particularly during critical events. Apollo 11 during its lunar descent had moments where the crew on the surface and mission control in Houston were essentially operating in parallel, each making decisions on their own information, exchanging communications that were always slightly out of sync with each other. Mars communications would be that effect, multiplied by 1,000 or more. 22 minutes is not a delay. It is a separation. It is the operational equivalent of being unreachable. In practical terms, this means that the Mars crew has to be largely self-sufficient. They have to make decisions in real time without consultation. They have to handle medical emergencies, equipment failures, weather events, psychological crises, all using only the expertise present on the crew itself, with no possibility of immediate ground support. This is a fundamental constraint on crew composition. The crew has to include medical capability, engineering capability, scientific capability, leadership capability, and psychological resilience, all in a group of perhaps 4 to 6 people. Every Mars mission proposal that has been seriously developed has wrestled with this. The crew has to be exceptionally cross-trained, exceptionally capable, and exceptionally able to function without support, and they have to do all of this while, on the surface of Mars, the most extreme weather event known on the planet can erase the entire infrastructure they depend on. Not destroy it gradually. Erase it. In one event, from a single phenomenon that has, in recent memory, ended a previous mission entirely. In June 2018, on the surface of Mars, a dust storm began to grow. NASA's Opportunity rover had been operating on Mars for nearly 15 years at that point. It had landed in 2004, planned for a 90-day mission, and had spectacularly outlived its expected lifetime. It had explored more than 45 kilometers of Martian surface, sent back hundreds of thousands of images, and helped transform our understanding of Mars's geology. It was solar-powered, drawing energy from panels that converted Martian sunlight into electricity for its systems. The dust storm grew larger over the following weeks. Within a month, it had become what Mars scientists call a global dust storm, a phenomenon that encompasses the entire planet, lifting fine dust particles into the atmosphere and blocking sunlight from reaching the surface. These global storms are not common, occurring perhaps once every several Martian years, but when they happen, they can persist for months. The 28th storm blocked enough sunlight that Opportunity's solar panels could not produce sufficient power to maintain the rover's systems. The rover went into low-power mode. Then it stopped responding to commands. NASA continued sending signals for months, hoping the storm would clear and the rover would wake up. The storm cleared in late 2018. The rover did not respond. In February 2019, after more than 1,000 attempts to make contact, NASA declared the Opportunity mission complete. The rover had not been damaged by the storm directly. Mars dust storms, despite the imagery in some science fiction, do not produce destructive winds. The Martian atmosphere is too thin for the wind to do much physical damage. What killed Opportunity was the dust itself, suspended in the atmosphere for months, blocking the sunlight the rover needed to maintain its battery and warm its electronics. Cold and lack of power over the duration of the storm made the rover non-functional. Now consider what this means for a crewed Mars mission. A global dust storm on Mars, by the time the first humans arrive, would not be a new phenomenon. It would be a known risk, factored into mission planning. But the implications for the mission would be severe. Solar power, if the mission relies on it, would be substantially reduced for the duration of the storm, possibly to the point of being insufficient for life support and equipment operations. The in-situ resource utilization plant, which requires significant power to manufacture return fuel, would slow or stop. The crew would be sealed inside the habitat with limited mobility for the months the storm lasted. If the mission is using nuclear power, the storm is less catastrophic but still consequential. The dust accumulates on equipment, on radiators, on solar panels, if any are present. It infiltrates everything. Mars dust is particularly fine, smaller than terrestrial dust particles, and electrostatic, sticking to surfaces and resisting easy removal. After a global dust storm, every external surface on the mission infrastructure would be coated in a layer of dust that has to be cleaned or worked around. A storm during a critical mission phase, such as fuel production for the return launch, could halt that production for months. If the storm is severe enough, fuel manufacturing might fall behind the schedule needed to fill the ascent vehicle in time for the return window. If the window is missed, the crew waits another 26 months. Another window, another opportunity, another set of risks accumulated during the extended stay. A storm during landing could be catastrophic. Spacecraft attempting to land during a global dust storm would have difficulty with their landing systems, which depend on accurate atmospheric data and clear visibility. A storm during ascent could similarly be disastrous. The Mars ascent vehicle, attempting to launch to a thick dust storm, would face conditions for which it has never been tested. This is the third wall in the cage. The first was radiation, a biological wall. The second was mass and engineering, a physics wall. The third is the environment itself, an unpredictable force that can disrupt or destroy the mission infrastructure at any time during the surface stay. The probability of a global dust storm occurring during any given Mars mission is not negligible. Mars seasons influence storm probability, and storms tend to occur during southern hemisphere spring and summer. A mission has roughly a 1 in 3 to 1 in 5 chance of encountering a global storm during a 500-day surface stay, depending on the season of arrival. The cage is now visible in its full shape. Biology says they cannot survive the radiation in good conscience by NASA's own standards. Engineering says the mass requirements to support return are at the edge of what is buildable. The environment says any of it could be erased by a storm. And yet, when you ask why anyone would go anyway, the answer turns out to be deep, historical, and connected to something humans have done for as long as we have existed as a species. Despite everything we have established tonight, despite the radiation that exceeds career limits, despite the engineering walls and the cost barriers and the dust storms and the psychological isolation, people will go. This is the strange, almost inevitable conclusion that emerges when you study the history of human exploration. People will go. They will sign up. They will volunteer for missions whose return is uncertain, whose risks are severe, whose costs to themselves are enormous. Not because they are coerced, not because they are unaware of the dangers, because there is something in the human pattern that has done this repeatedly throughout our species' history, and it shows every sign of doing it again with Mars. The Polynesians, between roughly 1500 BCE and 1200 CE, sailed across the Pacific Ocean in canoes made of wood, carrying entire family groups across distances they could not see across. They did not know what was on the other side. They did not have charts. They had stars, ocean currents, bird migrations, and an oral tradition that taught them to navigate by reading the patterns of the sea itself. They settled Hawaii, New Zealand, Easter Island, and dozens of other islands across millions of square kilometers of open water. Many died on the way. Many ships were lost. They kept going. The Pilgrims, on the Mayflower in 1620, crossed the Atlantic Ocean in a single small ship, planning to settle land they had never seen, in a climate they did not understand, among indigenous peoples they did not know. Of the 110 passengers who arrived at Plymouth, roughly half died in the first winter. The survivors planted crops, built shelters, and persisted. Within a few generations, the settlement had become permanent. The pattern repeats across every continent humans have ever moved to. The Bering Land Bridge crossings, the African migrations, the Polynesian sea voyages, the Atlantic crossings of the European settlement era, the American westward expansion. In every case, the first arrivals knew they were going one way. They knew they might die. They went anyway. The aerospace engineer Robert Zubrin, founder of the Mars Society, has spent decades arguing that this same pattern will apply to Mars. He developed the Mars Direct Architecture in the 1990s, a low-cost approach to crewed Mars missions that has influenced essentially every serious mission concept since. Zubrin's argument is that humans are settlement builders by nature. We have done it on every continent of Earth. We will do it on Mars, and on every world we can reach beyond Mars, because the impulse to explore and settle is, in his view, not just cultural, but biological. When NPR interviewed Buzz Aldrin and Schulze McCutcheon Davies about their one-way Mars proposal in 2010, they noted that they had no shortage of volunteers. Schulze McCutcheon reported that informal surveys among scientists and engineers found significant numbers of people, many of them with relevant technical expertise, who would volunteer for a one-way Mars mission if it were offered. The 2013 private Mars One project, which proposed exactly such a mission, received over 200,000 expressions of interest from people willing to sign up to go to Mars and not return. Mars One eventually failed for financial and technical reasons. The mission architecture was scientifically questionable, and the funding never materialized. But the demand it revealed, the willingness of substantial numbers of people to volunteer for a one-way mission to another planet, was real. The pattern of human willingness to attempt one-way migrations is not a relic. It is current. The first humans on Mars, when they go, will likely have volunteered knowing the risks. They will have been selected from a much larger pool of candidates. They will know what they are agreeing to. The radiation, the bone loss, the isolation, the 500 days on the surface during which return depends on technology that may or may not work as planned. The possibility that the return mission, when it comes time to launch, will not be able to launch at all. They will know these things, and they will sign up anyway. This is the strangest part of the story. The cage is real. Everything we have discussed tonight is real. And yet, when the opportunity arrives, there will be no shortage of people willing to step into the cage and go. What they will arrive at is a planet that, while reachable, is fundamentally hostile to the kind of life they bring with them. A planet where the very air would, on contact with their bare skin, do something most people do not realize is even possible. If you removed your suit on the surface of Mars, the first thing that would happen is not freezing or suffocation. It would be your blood beginning to boil. This sounds like a science fiction exaggeration. It is not. The Martian atmosphere is approximately 0.6% of Earth's atmospheric pressure at the surface. In Earth units, the pressure averages around 6 millibars compared to Earth's 1013 millibars at sea level. This pressure is below what is called the Armstrong limit, named after the United States Air Force physician Harry Armstrong, who in the 1940s identified the altitude at which atmospheric pressure becomes so low that water within the human body begins to boil at body temperature. Water boils at a temperature that depends on the pressure surrounding it. At Earth sea level pressure, water boils at 100 degrees Celsius. At lower pressures, the boiling point drops. At very low pressures, water boils at temperatures as low as 0 degrees Celsius. The Armstrong limit, around 19,000 meters of altitude on Earth, corresponds to a pressure low enough that water in the body, particularly in saliva, mucous membranes, and the moisture around the eyes begins to vaporize at human body temperature. The Martian surface pressure is roughly equivalent to an altitude of about 32,000 meters on Earth. Far above the Armstrong limit, an unprotected human on the Martian surface would, within seconds, experience the bodily fluids in their mouth, eyes, and skin beginning to vaporize. They would lose consciousness within about 15 to 20 seconds. They would die within minutes. This is not a slow death. It is the kind of catastrophic environmental failure that any breach of a suit, any failure of pressure containment, any moment of exposure to the actual Mars atmosphere produces almost immediately. Suits are not optional. They are absolutely required. Every external activity on Mars for every member of the crew, for every moment of the 500-day surface stay, requires pressurized suits and life support systems. And those suits have to work consistently. A suit failure on Mars is not like a suit failure on the Moon, where Apollo astronauts could potentially climb back to the lander before losing consciousness. A suit failure on Mars, particularly far from the habitat, would likely be fatal before the crew member could return to safety. The thin atmosphere does not provide enough air to breathe. The temperature is far below freezing. The radiation is significant, and the pressure is below the Armstrong limit. Beyond the pressure problem, the atmosphere also lacks something crucial: oxygen. The Martian atmosphere is approximately 95% carbon dioxide. The remainder is nitrogen, argon, and trace amounts of other gases, including oxygen at about 0.13%. This is essentially no oxygen. To breathe on Mars, you must carry your own supply, just as a deep-sea diver carries an air tank. The MOXIE experiment we discussed earlier was demonstrating for the first time that oxygen could be extracted from the Martian atmosphere at small scales. But for breathing, all the oxygen used by the crew must either be brought from Earth or manufactured on Mars in sufficient quantities to sustain them through the entire surface stay. The temperature ranges add another layer. Mars surface temperatures vary substantially based on latitude, season, and time of day. The equator can warm to about 20 degrees Celsius on a summer afternoon. The poles can drop to below -125 degrees Celsius in winter. Average global temperatures are around -63 degrees Celsius. The temperature swings between day and night can exceed 100 degrees in a single sol, the Martian day. Equipment exposed to this thermal cycling expands and contracts continuously, accelerating failure modes. Even without the pressure issue and the oxygen issue, the temperature alone would make Mars inhospitable to unprotected human life. With pressure, oxygen, and temperature all working against the visitor, Mars is, in every sense of the word, environmentally hostile. But this is not the only problem the atmosphere causes. The thin atmosphere is also the reason the surface is exposed to far more cosmic radiation than Earth's surface receives. The atmosphere of Earth absorbs and scatters most cosmic radiation. The Martian atmosphere does not. And this brings us to a problem deeper than any of the others. A problem rooted not in current conditions, but in the planet's geological history. A problem that started roughly 4 billion years ago and that no human visit can ever solve. Around 4 billion years ago, something fundamental changed in the deep interior of Mars. The planet, in its earliest period, had a hot molten core. The flow of conductive material in that core, like the flow of conductive material in Earth's core today, generated a global magnetic field. This magnetic field surrounded Mars in a magnetosphere similar in principle to the one that protects Earth. The field deflected charged particles from the solar wind, prevented atmospheric stripping, and kept the planet relatively shielded from the radiation environment of deep space. Then the core cooled. The exact cause of the cooling is still debated. Some models suggest that Mars, being smaller than Earth, lost interior heat faster. Some suggest that giant impacts disrupted the dynamo mechanism in the core. Some suggest a combination of factors. What we know with reasonable confidence from magnetic remnants preserved in Martian rocks is that the global magnetic field collapsed roughly 3.5 to 4 billion years ago. Mars, since then, has had no significant global magnetic field. The consequences have been severe. Without a magnetic field, the solar wind, a continuous stream of charged particles from the Sun, has been stripping Mars's atmosphere away for billions of years. NASA's MAVEN mission, launched in 2013, has measured this ongoing atmospheric loss. Mars currently loses approximately 100 grams of atmosphere per second to space, blown away by the solar wind because there is no magnetic field to deflect it. Over billions of years, this process has reduced what was likely a thick early atmosphere to the thin remnant we observe today. The reason Mars is now too cold for liquid water, too dry, too thin-aired, traces directly back to that lost magnetic field. The planet, without its dynamo, became unable to retain its atmosphere. The atmosphere thinned. The pressure dropped. Water that had previously existed as liquid on the surface either escaped to space or froze. Mars, over geological time, became what it is now, a cold, dry, low-pressure world stripped by the very solar wind that Earth's magnetic field continues to deflect. For human visitors, the missing magnetic field has another consequence. Cosmic radiation, the same galactic cosmic rays we discussed earlier, reaches the Martian surface far more easily than it reaches Earth's surface. Earth's magnetic field, together with its dense atmosphere, reduces surface radiation to manageable levels for everyday biology. Mars has neither effective protection. The surface dose, while lower than the in-space dose, is still significantly higher than anything humans evolved to handle. NASA's measurements indicate that the radiation dose on the Martian surface is roughly 64 millisieverts per day, or about 234 millisieverts per year. This is approximately 78 times the average annual background radiation that a human on Earth's surface receives. Cumulatively, over a 500-day surface stay, the radiation dose would be around 320 millisieverts, plus the cumulative cruise radiation, plus the return cruise radiation. This is the radiation dose that, combined with the cruise dose, brings the total mission exposure to roughly the 1 sievert mark we discussed at the climax of the radiation problem. The reason the surface dose is so high is, fundamentally, the missing magnetic field. Without it, the cosmic rays that have been deflected by Earth's magnetosphere have full access to the surface of Mars. This is not a problem that can be engineered around at the surface level. The Sun cannot be shielded by anything we can build on the planet's surface. The cosmic rays cannot be deflected by a small-scale magnetic field. The only effective shielding is mass, or distance from the source. Mass means meters of regolith, or water, or hydrogen-rich material between the crew and the sky. Distance from the source means getting underground. This is why almost every serious long-term Mars habitation proposal involves building either underground or under shielding made of Martian regolith. The first humans on Mars will likely not live in domes on the surface. They will live, at least primarily, in habitats covered by several meters of Martian soil or in natural underground structures already present on the planet. And it turns out, those natural underground structures exist. They have been identified from orbit, photographed, mapped. They may, in fact, become the homes of the first humans on Mars. Not because anyone wants to live underground, because given everything we have just described, living underground may be the only viable option. On Mars, scattered across the planet's volcanic regions, there are openings in the surface that lead to enormous underground passages. These are called lava tubes. They form on planets with active volcanism when underground rivers of molten lava cool, leaving behind hollow tunnels beneath the surface. On Earth, lava tubes exist in volcanic regions, Hawaii, Iceland, the western United States, and they are typically a few meters to tens of meters across. The lava tubes on Mars are different. The lower gravity allowed them to form at much larger scales. Some Martian lava tubes are hundreds of meters across, some are kilometers long. They are some of the largest known natural underground structures in the solar system. NASA's Mars Reconnaissance Orbiter has photographed openings into these tubes, called skylights, where the roof of a tube has collapsed and revealed the cavern below. The skylights show shadows that extend deep into the planet's subsurface. The lava tubes, sealed except for the skylights, are protected from cosmic radiation by the rock above them. They maintain more stable temperatures than the surface, varying less between day and night. They are sheltered from dust storms. For human habitation on Mars, lava tubes are extraordinary natural resources. Several recent studies have proposed that the first human bases on Mars should be located inside lava tubes. The radiation protection alone would be substantial. Several meters of basalt rock overhead reduces cosmic radiation dose by orders of magnitude, potentially bringing it down toward Earth's surface levels. The temperature stability would reduce the thermal stress on equipment. The sheltered environment would protect against dust storms. The volume available would allow for substantially larger habitats than would be practical to construct on the surface. This is in many ways an excellent solution to several of the problems we have been discussing. But it introduces something new. The first humans on Mars, if the lava tube approach is adopted, would live underground for years, possibly for the rest of their lives. This is not the heroic image of pioneers walking under an alien sky. This is the practical image of human beings in a cave on another planet, in dim artificial light with limited views of the outside world, going about their daily lives in an environment that is the opposite of every environment human beings have ever evolved to live in. We did evolve from cave-dwelling ancestors. Caves have been human habitats throughout much of our prehistory, but we evolved to leave the cave during daylight, hunt and gather under the sky, return at night. The daily cycle of light and darkness is wired deeply into our biology, into our circadian rhythms, into our hormonal cycles, into our mental health. A Mars cave habitat reverses this. The crew might emerge to the surface for limited periods, in suits for short excursions. Most of their time would be spent inside. Underground, the sun, when they could see it, would be dimmer than at Earth, because Mars receives less than half the solar irradiance Earth does. The sky would be brownish pink rather than blue. The horizons would be limited by the local terrain. For psychological health, this is not a benign environment. Studies of submariners, of Antarctic researchers, of people who spend extended periods in low-light environments consistently show effects on mood, sleep, hormonal balance, and cognitive function. The Mars crew would experience similar effects, possibly more severe, because their isolation would be more complete and their exposure to natural light more limited. The crew might adapt. Humans have proven remarkably capable of adapting to extreme environments over the long term. The crews of submarines and Antarctic stations function effectively over months. The ISS crews function effectively over 6-month rotations. But a Mars crew, if the architecture is one way and the timeline is decades, would not have rotations. They would not return to Earth for recovery. They would be permanent residents of an underground habitat on another planet, with their daily lives shaped by the practical realities of low light, limited mobility, and constant attention to the life support systems that keep them alive. This is what living on Mars actually looks like. Not the dramatic vista of an alien horizon, lived out by people who walk freely across red plains. Mostly, life inside a cave with periodic excursions in suits, sustained by power plants and resource utilization plants, and a long supply chain that stretches all the way back to Earth. And inside that cave, over years, the bodies and minds of the first humans on Mars will continue to change. They will adapt. They will become, in some real sense, different from the people who left Earth. And the question of whether they could even return, if the opportunity arose, becomes biological as well as logistical. Consider, for a moment, what a human body experiences over decades in 0-30 Go. We have already discussed the short-term effects: bone loss in microgravity, muscle loss, cardiovascular deconditioning. These effects, while severe, have generally been studied over periods of months. The long-term effects, over years and decades, are essentially unknown, because no human has ever lived for years in reduced gravity. We have predictions, models, hypotheses. We do not have data. What the models suggest is that human bodies adapted to long-term Mars gravity would, over time, become quite different from human bodies adapted to Earth gravity. The bones no longer required to support full Earth weight would adjust to the lower load. Bone density in weight-bearing bones would settle at a lower equilibrium than on Earth. The skeletal architecture might shift. The body might become taller, because the spine no longer carries the same compressive load. Some models suggest that humans living in lunar or Martian gravity for years could end up several centimeters taller than they would have been on Earth. The cardiovascular system would adjust. The heart, no longer required to pump blood against full Earth gravity, would become less powerful. The pressure regulatory systems calibrated to Earth conditions would recalibrate to the lower gravity. The fluid distribution in the body would shift. The face would, over time, look different because of changes in fluid retention and pressure dynamics. The muscles would adapt, particularly the postural muscles, the ones that on Earth maintain the body's upright position against full gravity. They would weaken, they would atrophy partially. They would settle at a strength sufficient for Mars gravity, which is less than the strength needed for Earth gravity. The implications for return are profound. A human who had lived for years in 38°, returning to 1G Earth, would experience Earth's gravity as crushing. The cardiovascular system, weakened for low-gravity operation, might be unable to maintain blood pressure against Earth gravity for sustained periods. Standing might be difficult, walking might be exhausting. Long exposures to Earth gravity might cause fluid accumulation in the lower extremities, cardiovascular strain, possibly more serious medical complications. For adults who spent years on Mars and then returned, the adjustment would likely be very difficult, requiring extensive physical therapy and possibly never being complete. For children born on Mars, or who spent their formative years there, the adjustment to Earth's gravity might be impossible. The skeletal and cardiovascular systems develop during childhood. A child whose body developed in 38G would have bones, muscles, and a cardiovascular system calibrated to that environment. Bringing such a child to Earth might cause immediate distress, possibly serious medical harm. This is speculative. There are no Mars-born humans. There may never be, but the speculation is grounded in well-understood physiology. The basic biology of how skeletal and cardiovascular systems develop and adapt is well known. The application of that biology to long-term Mars residents yields predictable patterns, even if the specific details remain uncertain. The implication is that beyond a certain duration on Mars, the question of return becomes biological. The crew is not just choosing not to return because of economics or engineering. They are physically incapable of safely returning. Their bodies have adapted to a different gravity field. Earth, for them, has become a planet they cannot survive on, at least not without significant medical intervention, and possibly never fully. This is the deepest version of the cage, not a logistical cage, not an engineering cage, a biological cage. The body itself, after enough time in the wrong gravity, becomes unsuited to its planet of origin. And remarkably, this is not a fantastical scenario. It is the predictable, slow, decades-long endpoint of any sustained human presence on Mars. The first generation who go to Mars as adults might be physically able to return if everything went well. The second generation who spend their formative years on Mars might not. The third generation who are born on Mars almost certainly cannot. Their home is Mars. Earth is the place their grandparents came from, a planet they have seen only as a blue dot in the sky. This is the line where Mars stops being a destination and starts being a home, and the question of return shifts from when will they come back to where do they come back to, because the answer, increasingly, is that they cannot. Let's return to the orbital mechanics, but with the accumulated weight of everything we have discussed tonight. The launch window from Mars back to Earth opens approximately every 26 months. We have established this. We have walked through the implications. We have discussed the 500-day surface stay that occurs between arrival and the first return window. Now consider what happens if you miss that window. The reasons a crew might miss their return window are numerous. The Mars ascent vehicle might fail to launch. The fuel production might fall short of the required quantity due to a dust storm or equipment failure. The crew might have medical issues that prevent launch. The vehicle might have suffered damage during the surface stay. Communications with Earth might have produced new instructions to wait. Any of dozens of possible failure modes could result in a missed window. If the window is missed, the next opportunity to leave does not arrive for another 26 months. During those additional 26 months, the crew continues to experience the radiation, the gravity effects, the psychological strain. The equipment continues to age. The fuel, if any has been produced, must be stored cryogenically for additional time. The infrastructure must continue to function. The supply chain from Earth must continue to deliver resources to keep the crew alive and the systems operating. And critically, the probability of additional failures increases. This is the compounding problem. Each window represents a chance to leave. Each missed window doubles the time of exposure, doubles the time of equipment aging, doubles the time of accumulated radiation, doubles the time of psychological strain. The probability of all systems functioning correctly for 2 windows in a row is lower than the probability of all systems functioning correctly for 1 window. The probability of all systems functioning correctly for 3 windows in a row is lower still. In probabilistic terms, if there is a 70% chance of successfully launching during any given window, there is a 49% chance of successfully launching by the second window if the first is missed, but only a 34% chance by the third window if the first 2 are missed. Each additional missed window subtracts from the total probability of ever leaving. This is the practical never. Not a physics never, a compounding probability that the longer the crew stays, the lower the chance becomes that they will ever be able to leave at all. The math here is brutal because so many of the variables we have discussed are interrelated. Equipment failure rates increase over time. Health problems accumulate. Psychological strain compounds. Fuel storage degrades. Dust accumulates on critical systems. The mass of supplies required to keep the crew alive grows. The cost to mission operations on Earth grows. The political will to maintain the mission after the original launch enthusiasm fades may diminish. Each window is a chance. Each missed window is a closing door, not just for that window but for some of the windows after it as well. Because the conditions for return get harder, not easier, with time. This is one reason why mission planners speak about the first Mars return window with such gravity. It is not just one window among many. It is the window. The first opportunity, when conditions are at their best, when equipment is freshest, when the crew is closest to its launch day physical condition, when the fuel supply has had the longest opportunity to be manufactured according to plan. After that window, every subsequent window has a lower chance of success. The honest projection is that if the first window is missed, the chance of any later window being successful is significantly reduced. By the third or fourth window, the chance of return may be functionally zero. The mission at that point transitions from a return mission to a permanent settlement, whether the crew or the planners intended that transition or not. This is what never actually means in the context of Mars return. Not a physical impossibility, a compounding probability sliding downward over time that eventually becomes indistinguishable from impossible. It is, in practical terms, a never, even if the universe does not technically forbid it. There is a careful distinction worth making at this point in the conversation. When we say the first humans on Mars would never return to Earth, we are not making a statement about physics. Physics does not forbid the return. The laws of orbital mechanics permit a Mars to Earth trajectory. The laws of chemistry permit the manufacturing of return fuel. The laws of biology permit human bodies to survive, with care, the radiation and the gravity changes. The laws of engineering permit, in principle, the construction of vehicles capable of completing the round trip. The never we have been describing is something else. It is the compounding of constraints, none of which alone is absolute, that together produce a practical outcome indistinguishable from impossibility. The radiation exceeds NASA's career standard. The Mars ascent vehicle has not been built. The in situ resource utilization plant has not been scaled. The mass that has to be landed exceeds current capability by an order of magnitude. The Mars sample return mission, which would have demonstrated unmanned return capability for a few grams of rock, has been effectively cancelled at $11 billion. The dust storms can disrupt mission infrastructure at any time. The bone loss and muscle loss accumulate during the cruise and may not stabilize on the surface. The psychological strain compounds over the 500-day stay. The launch windows open every 26 months, and each missed window compounds the difficulty of subsequent attempts. Each of these, individually, is not insurmountable. The radiation can be reduced with shielding, with development of effective drugs, with potentially nuclear propulsion to shorten the cruise time. The ascent vehicle can be developed over a 15 to 20-year program. The ISRU plant can be scaled. The mass can be landed with new technology. The dust storms can be planned around. The psychological strain can be managed. The launch windows can be hit if everything else works. But together, all of them, in a single mission with a single crew in a single time period, Working within a single budget is the constraint that becomes unmanageable. Any one of these problems is hard. All of them together, simultaneously with no failures, is not what realistic engineering looks like. So when serious aerospace engineers say the first humans on Mars will not return, they are not making a physics claim, they are making a practical claim. They are saying that the probability of all the necessary technologies, infrastructures, and conditions converging successfully at the same moment in a way that permits return is low enough that it is more realistic to plan for non-return than to plan for return. This is not a defeatist position. It is a clear-eyed one. It allows mission planning to focus on what is actually achievable, get the crew to Mars, sustain them there, build infrastructure that supports their continued life, add additional crew over time, develop return capability if and when the technology becomes practical, which may be decades after the first crew arrives. This framing turns the problem from impossible to tractable. By accepting one way, the architecture becomes achievable. By insisting on round trip, the architecture remains at the edge of feasibility, possibly forever. The never is honest. It is also, paradoxically, the path that makes the mission possible at all. And this is why some of the most experienced people in space exploration, when they think carefully about Mars, arrive at one way as the realistic answer. Not because they want it that way, not because they think the crew should never return, but because the math, when honestly examined, points there. The first humans on Mars will likely not come back. That outcome is not because the universe forbids return. It is because the universe makes return so much harder than going that, given the realities of how missions are funded, designed, and executed. The practical outcome is one way. This is the honest answer to the title of tonight's conversation. They would never return. Not because they cannot. Because when you stack all the realities together, the math says they will not. And what they would have instead is a view of Earth from the surface of Mars that no human has yet seen with their own eyes, but that has been photographed, and that captures in a single image what staying actually looks like. On January 30, 2014, NASA's Curiosity rover, sitting in Gale Crater on Mars, raised its camera and took a photograph. The image shows a dark Martian sky shortly after sunset. The brown-pink horizon line cuts across the lower portion of the frame. Above the horizon, against the deepening sky, there is a single bright point of light, larger than the surrounding stars, distinct, plainly visible to the naked eye if a human were standing in Curiosity's place. That point of light is Earth. This is the first photograph ever taken of Earth from the surface of another planet. Specifically, the first photograph ever taken of Earth from the surface of Mars. The image is striking in its simplicity. A planet, a sky, a plaintive light. Everything that has ever happened to every human being who has ever existed, every conversation, every meal, every birth, every death, every dream, every disappointment, every love, every loss, all of it, compressed into a single bright dot on a Martian horizon. The astronomer Carl Sagan, in 1990, wrote famously about a photograph the Voyager 1 spacecraft had taken of Earth from beyond the orbit of Neptune. He called Earth in that image a pale blue dot, a phrase that has since become one of the most quoted descriptions of our planet's place in the universe. The Curiosity photograph is the same image from a different angle, Earth, seen from another world, reduced to a single point of light. For the first humans on Mars, this view will be daily. They will look up. They will see Earth in the Martian sky, sometimes brighter than any other star, sometimes obscured by the dust of an approaching storm, sometimes vanishing entirely below the horizon during certain parts of the Martian year. They will know, looking at that dot, that everyone they have ever known is there. Their parents, their siblings, their friends, their children, if they had children before leaving, the places they grew up, the streets they walked, the trees they climbed, the oceans they swam in, the cities they lived in, all of it, compressed into a point of light, and they will know that the dot is essentially unreachable, not because it is far, though it is, not because the journey is impossible, though it is nearly so, but because for them, given the conditions of their mission, the cage of compounding constraints we have walked through tonight, Going back is not a real option. This is the emotional weight that cannot be calculated. The technical analyses we have done tonight, the radiation doses and the launch windows and the Tsiolkovsky equation and the dust storms are all real and important. But for the actual humans who would be on Mars, the practical reality of not returning is summed up in this single image. Earth as a dot in the sky. Familiar. Visible. Out of reach. The crew would adapt. Humans adapt to remarkable circumstances. They would find purpose in their mission, in the science they are doing, in the infrastructure they are building, in the legacy of being the first human residents of another world. They would build relationships with each other. They would communicate with Earth asynchronously across the light delay. They would receive messages from family. They would send messages back. The communication would not be conversation, but it would be contact. And every clear Martian evening, when the dust settled and the sky was clear and Earth was on the right side of the sun, they would step outside, in their suits, and look up, and see the dot. And remember, this is what choosing to go to Mars actually means. Not just the dangers, not just the constraints, the specific daily reality of seeing the planet you came from as a point of light, and knowing that the distance, in every practical sense, is uncrossable from where you stand. Some would find this devastating. Some would find it liberating. Some would find both at different times. But all of them, if they go and stay, would learn what it feels like to look at home from a place that home cannot reach. That is the inner reality of the one-way mission. Not heroic exactly, not tragic exactly. Something else, something that humans have done before in different forms throughout history, and that we are likely to do again on Mars when the time comes. If you step back from the technical details, from the radiation doses and the launch windows and the engineering walls, there is a quieter pattern visible in this story. The one-way mission is not a tragedy. It is not a failure of imagination or engineering. It is the historical norm of every settlement humanity has ever attempted. The Polynesians who sailed across the Pacific in their canoes, settling islands across millions of square kilometers of open water, did not return to Taiwan or to wherever they originally came from. They built lives on the islands they reached. They had children. Their children had children. Over generations, their descendants became the local population. The pattern was one way, not because they were forced, because that was the practical reality of voyaging in canoes across open ocean. Coming back was harder than going, so they did not. The Pilgrims who landed at Plymouth Rock in 1620 did not, with very few exceptions, return to England. They had crossed an ocean in a small ship, planned to build a settlement, and stayed to build it. Many died in the first winter. Those who survived persisted, were joined by additional ships, and slowly built what would eventually become a permanent settlement. The pattern was one way. The settlers came to stay. Across human history, on every continent we have ever settled, the pattern repeats. The first arrivals went one way. The return trip, when it was even possible, was rare. The defining characteristic of human migration has been departure without expectation of return. This is the perspective the one-way Mars proposal sits within, not a science-fictional extreme, not an ethical violation, the continuation of the most consistent pattern in human history. The first humans on Mars, going one way, are participating in something that humans have done since we emerged as a species and began to move across landscapes that our ancestors could not have imagined. The proposal becomes less shocking, less harsh, less extreme when placed in this context. It also becomes more honest. The Mayflower Pilgrims, the Polynesian voyagers, the Bering Land Bridge crossers, none of them had any guarantee of survival, much less of return. They went anyway. They built. They persisted. And what they built, eventually, became home. A one-way Mars mission, in this light, is not a departure from the human pattern of exploration. It is the natural extension of that pattern to a new world. The first crew arrives knowing they will not come back. They establish a habitat. They begin to survive on local resources. They are joined over time by additional crews. Over decades, a small permanent community develops. Eventually, perhaps, that community becomes self-sustaining enough that travel between the planets becomes routine rather than heroic. This is the long view. It is not the view that most public conversations about Mars adopt. Most conversations focus on the dramatic first crew, the round trip, the celebrated return. But the technical realities, the realities we have walked through tonight, point toward a different model, a model where the first crew is the founding crew of a permanent settlement, where return capability comes later, gradually as the settlement matures, where the relationship between Earth and Mars evolves from a series of dramatic missions to something more like the relationship between any two settled places. Travel possible, travel routine, but not the defining purpose of being there. This is what one way means, properly understood. Not abandonment, not exile, settlement. The same thing humans have done on every world they have ever moved to throughout our species' history, and the first humans who agree to this, who volunteer for the one-way journey, will not be doing something extraordinary by historical standards. They will be doing something that humans have done thousands of times before. They will be the latest in a long line of pioneers who went somewhere new, knowing they would not come back, and built lives there anyway. When they look up at the dot in the sky, at the Earth they came from, they will be doing what every settler in human history has done at some point during their voyage, looking back at where they came from and choosing, despite everything, to continue building where they are. This is the quiet honesty of the one-way mission. Not glorious, not tragic, simply the structure of every truly new place humans have ever chosen to enter. We have walked tonight through what it actually means to send humans to Mars. We have looked at the distance, an average of 226 million kilometers, never the same twice, governed by the eternal dance of two planets around a sun. We have looked at the 26-month rhythm of launch windows, set by orbital mechanics that do not negotiate. We have looked at the 500-day surface stay required by that rhythm, longer than any deliberate human isolation ever conducted. We have looked at what the journey does to the body, the bone loss in microgravity, the muscle atrophy, the radiation exposure that exceeds NASA's career standard in a single mission, the 0-38G problem that may or may not allow the body to maintain itself during the surface stay. We have looked at the engineering walls, the Tsiolkovsky equation that makes carrying return fuel from Earth impractical, the Mars ascent vehicle that has never been built, the in-situ resource utilization technology that works at experimental scale but not yet at mission scale, the mass that has to be landed on Mars before the crew can plausibly attempt to return, beyond current capability by an order of magnitude. We have looked at the economics, the $11 billion that could not bring rocks home, the 3 to 10 times multiplier that return capability adds to mission cost, the serious proposals from people who have spent careers thinking about this, that the only practical path forward is one way. We have looked at the inner realities, the psychological strain documented in Mars 500, the 22-minute communication delay, the dust storms that can erase infrastructure, the need to live underground, the decades of adaptation that change human bodies into something not quite fitted for Earth anymore. And we have arrived, through this long walk, at the honest answer to the title of tonight's conversation. The first humans on Mars would never return to Earth. Not because the universe forbids it, because the universe makes it so hard that, when honest engineers and biologists and economists do the math, the practical answer is one way. The cage is real. The cage is built from compounding constraints, not absolute physics. And the cage, while not literal, is functionally indistinguishable from a true prohibition. This is what they will arrive to. A planet they cannot leave. Not as an emergency, but as a feature of the mission they signed up for. A view of Earth as a dot in the sky. A community, eventually, of fellow pioneers. A new home, in the most literal sense, built from scratch on the surface of another world. And maybe, in that view, in that dot in the sky, there is something quieter than tragedy. Something that the Pilgrims looked at as they sailed away from Plymouth, England in 1620. Something that the Polynesians felt as they looked at the islands disappearing behind them on their canoes. Something that every human pioneer, on every world humans have ever moved to, has felt at some point during their journey. The honest journey may be the one-way one, not the heroic round trip, The quiet, deliberate, knowing choice to go somewhere new and build a life there, accepting that the place you came from is now a place you have left. The first humans on Mars may never come back, and that may be, in its own strange way, the most honest journey any human has ever taken. The rest of the night is yours.